Okay, good morning. This particular little dorky video is designed to give you just a little bit extra practice in interpreting chemical formulas, especially the complex ones with lots of, I don't know, parentheses and coefficients and stuff like that. So if you already know how to do that, then you probably don't want to watch this video. But if that was something that you covered, still a little weak on, then this is a good place for you to kind of get a little bit of extra practice on kind of how to interpret those. So first thing, just as a basic part, don't forget, in terms of reviewing subscripts. Subscripts are the little numbers, the little ones that hang down below. They only attach to that particular number next to it. So I'm going to kind of point to some of these examples here on the screen. We've got MgCl2 up here on the left. And just as a way of kind of a strategy I want to show you, you can kind of draw these out a little bit. Once you understand sort of what these numbers mean, you can kind of represent them like using the little circle models like is over there on the left. So MgCl2, what that means is that there's one magnesium atom and then there's two chlorine atoms, and that 2 only applies to the chlorine. So if we don't put a subscript there like on magnesium, we assume that there's one of them present, otherwise why would we bother writing it? So if we take a look at some of these more complex ones on this particular screen, like H3PO4, there's a different version of they call it a ball and stick model, but there's a different version of a model that we can use to represent that. So the little white circles here represent hydrogens, there's a phosphorus in the middle, and there's 1, 2, 3, 4 oxygens that are on that particular thing. So H3PO4 means there's 3 hydrogens, 1 phosphorus, and 4 oxygens to it. Down here, NH4NO3. A good example of some of these last couple of things, that when I ask you to tell me the numbers of atoms of something, don't forget to add together any atoms that are repeated. Like, for example, in this one, nitrogen, the N, appears twice in this formula. So that means when I ask you the total number of atoms of everything, you need to add those two together. So if I ask you how many nitrogens there are, you should tell me that there's 2 total nitrogens. There's 4 hydrogens, and there's 3 oxygens. You wouldn't say there's 1 nitrogen, 4 hydrogens, 1 nitrogen. So when you're doing a sum total, again, if it appears more than once in the formula, there's a reason for it. It has to do with the structure of it, but when I'm just asking you a total number of atoms to combine them. So this last one on the right, CH3COOH, again, it looks a little weird that things are kind of written out. They're not really combined together. But again, it's due to the structure of it. And you can kind of see that in that little ball and stick model that's down there. So it's CH3, that first thing that's there has got a carbon and 3 hydrogens next to it, and then there's a carbon, and then there's 1 oxygen bonded to it, and then there's a second oxygen and a hydrogen bonded to it. So that's why it's written out as COOH. But your totals, there's 1, 2, 3, 4 hydrogens total, there's 1, 2 carbons total, and then there's 1, 2 oxygens total. So again, if you're looking at subscripts and more complex ones, don't forget to combine any elements that appear more than once in a formula. Okay, so why do we even care about this? Why do we have to worry about what the formulas are? It turns out the formulas actually is really important. The way that a formula is written tells us something about the molecule or the compound itself. The formulas are different for different compounds, and different compounds can have the same elements in it. So that can get really kind of confusing if you just leave those out of there. So, for example, that top left picture right there that's got the orange and the black and the yellow stuff in there, those are all iron and oxygen. We could call them all iron oxide, but yet they have 3 different formulas and 3 different colors to them. They're very different characteristics chemically as well. So it's kind of important to make sure we don't just drop those off. We can't just call it FeO, because they actually are molecularly different, and that chemically is different too. The one that you guys know as rust is that one that's over on the left, Fe2O3. But those other versions of iron are also out there, and they're important in rocks and paint and all kinds of other stuff that we use them for. Bottom on the right is another example of one. There's a couple of different common compounds that are made of hydrogen and oxygen. And it's really important to know which one you've got, because H2O is one thing, and H2O2 is something else. One you'd want to have a glass of, one not so much. So make sure that when you write those subscripts down there, you're actually telling us something very important about which compound it is. So you can't just drop those off. You can't just leave them out there. They do give us really critical information about which exact compound it is, and then that can really make some differences. Like I said, you wouldn't want a big old glass of hydrogen peroxide. Not delicious. Okay. So creating simple formulas. Don't overthink this. At this point, it's just going to be like a little paragraph that's going to describe to you what atoms go there, and just can you put the subscripts in the right place and not use them like exponents. So please don't overthink this part. We'll be making formulas based on chemical information later on. This is not the time for that. So if you can see down below that second thing, it says write the formula for a compound containing 6 atoms of carbon, 12 atoms of hydrogen, 6 atoms of oxygen. all you got to do is write it pretty much exactly like it says. So it starts with 6 atoms of carbon, so I'd write C6. The next thing is 12 atoms of hydrogen, so you can probably guess what I'm going to write, an H with a 12 after it. And then finally there's going to be 6 atoms of oxygen, which is going to be an O with a 6 after it. So again, just basic applications. Can you interpret the paragraph, put them in the same order, and exactly just write them out like it says. So if you want to, for practice, you can hit pause and try to do the one at the bottom about potassium, sulfur, and oxygen. If not, I'm going to go through it right now. So hit pause. Yes, no? No? Anyway. So here's the formula. 2 atoms of potassium would be K2. 1 atom of sulfur would just be the letter S. And then 4 atoms of oxygen, an O with a 4 after it. So simple formulas at this point in time, just can you go the other direction? Okay, more difficult ones, dealing with parentheses. These are always kind of a pain. One of the things that we've got to understand here is that when there's parentheses present in a formula, it's because there's a group of atoms that's being doubled up or tripled up, so to speak. So I'm going to start with the MgOH2 that's on the left here. Here's a diagram of what it actually looks like, and sometimes that kind of helps to interpret what that formula means. It means there's a magnesium in the middle, and then there's an OH on one side, and then there's another OH on the other side. So that's why it says OH2, because there's 2 OH groups that's on there. So when we say the number of atoms that are present on this, we count them all up individually. The subscript works like a multiplier, I guess. So you'd have 2 times oxygen and 2 times hydrogen. So here's your kind of accounting sum to it. In MgOH2, there'd be 1 magnesium, 2 oxygen, 2 hydrogen. So they do get a little bit more complex, so we'll go through some of these other examples here. So barium, BaNO3, it's called barium nitrate is the name of that. So that means you've got a barium, and then that group NO3, there's got to be 2 of them. So there's an NO3 and another NO3. So here's what it would look like if I drew it out. Something kind of like that. Don't worry too much about the plus, minus, and the lines and all that, but you get the idea that at the top there's an N with 3 O's, at the bottom there's an N with 3 O's, and there's a barium right in the middle. And that'll help you count them out if you need to. So our final accounting on here, we should have 1 barium, and then those NO3s, we have to count them up twice. So we should have a total of 2 nitrogens, 1 from each, and then a total of 6 oxygens, 3 from the top group and 3 from the bottom group. Okay, this last one over on the right, the name of this thing is ammonium carbonate. It's NH4 CO3. So hopefully you can picture in your head there's an NH4 and another NH4 and then a CO3 or a C and an O3, something like that. So there's the crazy picture of that thing in terms of what it would look like. So now I should be able to kind of count out in terms of what there is. So total of this, NH4 2 means I multiply that across 2 nitrogens and then 2 times 4 hydrogens, so that's a total of 8. And you can see those in the picture. There's 1, 2, 3, 4 hydrogens, 1, 2, 3, 4 hydrogens. And the CO3 should be pretty straightforward to interpret it, 1 carbon and 1, 2, 3 oxygens. So there's our final accounting of that one. We should have 2 nitrogens, 8 hydrogens total, 1 carbon and 3 oxygens. So again, once you get the hang that the parentheses is a group of atoms, and then a subscript outside those parentheses applies to the whole group, it's a multiplier. Sometimes drawing it out can help, but it isn't too bad after a few minutes. Okay, moving on last little bit, if we're starting to talk about coefficients, we'll get into this more in balancing equations. I just want you to be able to kind of identify it. When we put coefficients, those are big numbers that go out in front, and a coefficient like 3CH4 over here on the left, it means I've got a CH4, a carbon with 4 hydrogens to it, it's called methane. But when I put a 3 out in front, that means I've got 3 of those entire molecules. So it's not just 1, it's not 2, but it's actually 3 of them. So the 3 in front acts like a multiplier when I do my accounting to it. So instead of just having 1 carbon, I have 3 times 1 carbons. And instead of having 4 hydrogens, I have 3 times 4 hydrogens. So there's your totals, 3 carbons and 12 hydrogens total in that entire molecule. All right, last but not least, over here, 2Al2SO43. Holy cow, if you can do this one, you're in really good shape. So this is be the quiz yourself time. Pause it and see if you can figure out what the accounting is, and then I'll run through it. If you don't want to pause it, I'm going to keep going here in a second. But see if you can kind of figure out exactly what's in everything there. Okay, this is a crazy diagram, frightening. So Al2SO43 means I've got an Al and an Al. You can see them possibly right there in the center of the big green circles. And then I've got 3 SO4 groups. There's one, there's a second one in the bottom center, and then there's a third one in the top left. So that's one molecule. It's a huge molecule. Got a lot of stuff in there. So our total accounting for this thing, for one of these, is going to have 2 aluminums, 1, 2, 3 sulfurs, and then 4 oxygens in each sulfur group times 3. So that's 12 oxygens total. There's 4, there's 8, and then there's 12 total. That's in one molecule. The 2 out in front, this coefficient, means I now have 2 times everything. So I have to double everything up. So there's my 2 molecules, and now you can start doing the counting if you want to, or here's what it actually looks like when we do it all out. You can use kind of a little formula if you want. If that doesn't work for you, don't worry about it. But you kind of multiply it out. The subscript numbers start there. You multiply it by a parentheses number if there is one, and then you multiply it by a coefficient. So our total accounting for this particular crazy molecule, we've got 4 aluminums because there's 2 in each molecule times 2 molecules. For sulfur, we've got 1 sulfur in each group times 3 of that group times 2 molecules total, which means 6 complete. And then oxygen is by far the worst. We've got 4 oxygens in each group. That's the subscript number. There are 3 of those groups. That's the number outside the parentheses. And there's a 2 coefficient, so there's 2 times everything. That gives us a total of 24. So if you can do that, you can do any of them. That's as hard as it gets right there. All right, so as a result of this little mini lesson, here's the things that we kind of looked at in a little bit more detail, kind of giving you that idea of using a drawing strategy if you need to, using little circles or just even letters, something to kind of sketch out what it is. It helps, especially with kind of larger molecules. Second thing, making sure you know why we have to do the subscripts instead of just their numbers, who cares, that they do actually give us different chemical types, I guess. Then being able to write simple formulas from a paragraph, again, that's pretty straightforward, I think. And then the last part here is really the big part. Can you actually use the whole process to deal with parentheses? Can you deal with subscripts? Can you deal with coefficients out front and do your final accounting? So I hope this helped if you need it. If not, I hope you weren't too bored. See you next time.